When we were dealing with polynomials, we were allowed to add, we were allowed to subtract, and multiply polynomials together and still have them be polynomials. However, when we take the quotient of a polynomial, that's to say when we divide two polynomials, we get functions with a lot different characteristics. So we don't characterize them as polynomials. We give them a different name. We call them rational functions. So that's when we have some function that is a quotient of two functions. So we have some polynomial in the numerator and some polynomial in the denominator. And the reason that we classify them differently is because in the denominator we can get zeros. And when we get a zero, we get an undefined function. And when we get an undefined function, there are going to be asymptotes, there are going to be holes in the graph. So when we have a polynomial, just some regular polynomial, to equal it is anx plus some stuff. The domain of this is all reals. Here the domain is not all reals. Here we're going to, whenever d of x is equal to 0, we're going to get an undefined point, a point that has no definition. That's why it's called undefined. And when we have an undefined point, let me just illustrate it real quickly. I'm not going to go into extreme detail in this video about asymptotes and holes. What I'm going to do is just go over them very briefly, and then in successive videos we'll go over each one individually. So an asymptote looks something like this. And here's some number that the function approaches but does not touch. It can get infinitely close to it, but it will never actually be whatever this number, let's just say a. We'll just call it a. It will never actually have a value of a. It can get, like I said, infinitely close. There's no way I can even describe how close it can get. It can get as close as you can think and then even closer. But it will never actually touch a. And another thing we can get when we have a 0 in the denominator is a hole in the graph. So we can just be going along and then all of a sudden there will just be some value that's just not there. So these kind of properties make it a lot different from polynomials. So let's just put some random polynomials up. Polynomials are continuous functions. That's to say that there are no breaks in the graph, and the graph is just one long line. Whereas to these rational functions over here, we can see that the graph is broken in two right here. There's actually two bits of the graph. So if this was the only asymptote, there would be the part of the graph that was on the left side of A and the part of the graph that was on the right side of A. These two ends never meet. And same if there was a hole in the graph. There would be the part of the graph that was to the left of the hole and then to the right. But these would never meet. Something like, I don't know, x squared plus 1. Look like this. And it has a domain of all real numbers, because for every x there is a y. There are no x values that we can put in that will give us the square root of a negative number or a 0 in the denominator. Now don't confuse this with finding the zeros of a function when we are using complex numbers. Finding the zeros of a function is to find out when an equation touches the x-axis. As we can see here, this does not touch the x-axis, so it does not have a real zero. But don't confuse finding the zeros of a function for the domain. Those are two different things. So here we're just talking about domain. And that's essentially all rational functions are about. They're really about the numbers that cause the domain to be 0, and then what happens because of it. So let's have a look at a few functions. I know this will be mostly review, but let's look at some anyways. Let's say we have f of x is equal to, I don't know, 5x minus 9 over x minus 1. And I want to know the domain. So the domain, we're looking for numbers that will give us a imaginary number, or that will give us a 0 in the denominator and therefore be undefined. And here, and in most other problems we're going to be dealing with, we're not going to be dealing with square roots. We're going to be dealing with zeros in the denominator. So here we can see that x cannot be equal to 1. So the domain is negative infinity to 1 and 1 to positive infinity. So let's do one more. Let's say f of x is equal to x over x squared minus 6. What's an easy number? 8. 6x. So let's find out what would make this equal to 0. So in order to find out what numbers would make this polynomial equal to 0, we have to find the zeros of this polynomial, and we are plenty of times going to be applying what we learned from the previous sections where we've been finding zeros of equations, because we need to find the zeros of equations to figure out what makes this function undefined. So this is an easy enough one. We need two numbers that multiply to be positive 8 and then add to be minus 6. Minus 2 times minus 4 is positive 8. Minus 2 plus minus 4 is negative 6. So actually, I don't need it squared. I don't know what I was doing. So this is the same as this. And we can use quadratic formula if you want. Some people I know are very uncomfortable or not very confident in themselves when just doing these functions by eye, or they're just not very good at it. And if that is the case, do not be afraid to use quadratic formula for everything and anything. There's nothing wrong with it. All this really does is just save time. But if you really are not good at it or just not comfortable with it yet, sometimes especially if you're in a school or something like that, then you have to go at the pace that they teach you. Whereas if you're learning on your own or educating yourself, then you can go at your own pace. But if you're at a school and you're not really comfortable doing it by eye, don't be afraid to use quadratic formula for everything. It does take longer, and by using quadratic formula, you're opening yourself to different types of mistakes. But quadratic formula will work. So just to know. So we can say that this is the same as x minus 2 times x minus 4. And now it's very easy to see that 2 and 4 are going to make this equal to 0, and therefore undefined. So we can say that the domain is equal to negative infinity to 2, 2 to 4, 4 to infinity. And notice here that 0 is in the domain. Just because the function is equal to 0, that's okay. Some people might decide that anything that makes this 0 is not in the domain. That's not true. It's just what makes it undefined, and that's only a 0 in the denominator, not any 0 in the numerator. So a lot of times, actually, when we're dealing with rational functions, we're going to be ignoring. Actually, let me do one more. Let me do one more example to drive home the point. Let's say I have f of x is equal to x squared minus 4 over x minus 2. So we can simplify the top if we would like to x minus 2 and x plus 4. And we have an x minus 2 in the denominator. Now it's very tempting, and we can do it if we want to, just to cancel these out and just say that the domain is all real numbers. But that's not true, because x cannot equal 2. This is a mistake that lots of people make. They just cancel these out and leave it as all real numbers, the domain. The domain is equal to negative infinity to 2, and then 2, oh, I forgot the u, then 2 to infinity. So we can simplify this and just say f of x is equal to x plus 2, as long as we write x cannot equal 2. Otherwise, then otherwise x plus 2 is just x plus 2, and why do we even need to write this? The reason that this isn't there, it's saying that the function is equal to x plus 2, but the only point that is not included is 2. So it is, while this function is very close, the graph of this function will look almost exactly the same as. And the only difference between these two graphs is going to be that there's going to be a hole in the graph at x is equal to 2. And I don't really want to go into detail on the difference between when we're going to get a hole in the graph as opposed to when we're going to get an asymptote. And there are different types of asymptotes. We can get vertical asymptotes, horizontal asymptotes, and even diagonal asymptotes. And we're going to be going into that in these next few videos. But just know that these are almost exactly the same, and the only thing that is different is that there's a hole in the 2. And that's why we have to specify that x is not equal to 2. Otherwise, then these are the same. This is the same as this, and they're not. So you have to be very careful not to cancel something out or to include a 0 because it's a 0 in the numerator by accident. And for most of the time, we're almost exclusively just going to be paying attention to the denominator. Probably about 90% of the problems, we're only going to be looking at the denominator, and the only time we're really going to be looking into the numerator is just to see if it's a hole or an asymptote.